Okay, so we're getting to the end of this here. In the last video, we talked about these attoclock experiments where people use attosecond laser pulses to look at this tunnel ionization phenomenon and seem to see data that are consistent with the time for quantum tunneling being zero, that the particle just shows up on the outside of the barrier without passing through the intervening space, taking no time to do it. These are spectacular experiments, really impressive work, but there's a little bit of ambiguity to this as to whether they're actually measuring the zero time that they think they're right. This is working right at the limit of the technique, right? And there's a little bit of ambiguity here, just enough to make this slightly questionable. So the question that we ended the last video with is, can we use ultra cold atoms to do a better experiment, to do something that would allow us to measure this tunneling time in a different way that doesn't have the same issues that we see with the attoclock experiments. There is, and that's what the group in Toronto has done, and so that's what we're going to talk about now. To explain this, what they're really after is kind of an idealized experiment, right? We want to reframe the question and saying, not how long does the tunneling take, but can we prove that the tunneling particle spends some amount of time inside the classically forbidden region? That it takes some time to cross the region where it shouldn't be found according to classical physics because its energy isn't high enough. If we want to answer this, the thing that we want kind of conceptually is a clock that only ticks when it's inside the barrier, right? So we have some sort of clock that's moving with our atoms, right? As they approach the barrier, the hands of the clock don't move. While the atoms are inside the barrier, if they're inside the barrier, the hands of the clock advance, and then as soon as they get out on the far side of the barrier, the hands of the clock no longer move forward. They stay at the same time. This is sort of the idealized thing that you want to answer this question of tunneling time. Is there, if we can have a clock that only ticks when the atom is in the classically forbidden region, then that would tell us how much time it's spending in that region. And removes the ambiguity about exactly when did it hit the beginning and when did it leave the barrier, right? You don't have to worry about the start and stop timing anymore. Just how much time does it take inside the barrier? So this is a thing we can make using atoms and their interactions with light. Now, how good a clock do we need? Well, again, we can do one of these back of the envelope estimates here and say, well, how long do we expect this to take, right? Is this going to be some absurdly difficult thing to do? And so we can estimate this. We say, well, the barrier they have is, roughly 1 micron in length. That's 10 to the minus 6 meters. What's the speed at which the atoms are moving? Well, we're starting with a Bose-Einstein condensate. Typically, the speeds at which those things are the atoms in those are moving are kind of millimeter per second kind of velocities. That's 10 to the minus 3 meters per second. If I want to say what's the time that it would take for an atom at a millimeter per second to cross a barrier that's a micron across, that's 10 to the minus 6 meters divided by 10 to the minus 3 meters per second. That's about a millisecond. Okay, so we're not talking about times here that are absurdly difficult, right? We don't need to be switching things on and off really fast, right? This is a time scale that is relatively easy to do with ordinary electronics, and this is sort of the time scale at which BEC experiments naturally operate, right? Times of milliseconds or tens of milliseconds is sort of what people normally do with these. So this is a relatively easy experiment in terms of what you're demanding of the electronic system. So how do you make such a clock? There are two pieces of this, and both of the pieces of the clock depend on the details of the level structure in rubidium. So rubidium, right, each of the states in the rubidium atom that we use for laser cooling has a number of sublevels. It turns out the upper state has 5 sublevels that are numbered -2 to +2. The lower state has 3 sublevels that are numbered -1 to +1. That has to do with the angular momentum of the electron in the orbit. It doesn't really matter for these purposes, just that they have these different levels. And you can shift these levels around by applying magnetic fields. So if you put a magnetic field on, some of the levels go up in energy, some of them go down in energy. The offset in the little picture here is showing you what that looks like. What they do for these experiments, you can also move the atoms between sublevels using laser light. Right, and so what they do is they pick two of these levels to be the sort of primary levels of interest. For historical reasons, they designate one of them as plus X and the other as minus X. We'll write them in these little half-angle brackets here. And those are the two states that they're particularly interested in. The energy separation between those two states is 6.8 gigahertz. That corresponds to a frequency in the microwave range. And the particular states they choose are the zero states that do not shift in the presence of a magnetic field, which just simplifies life. They don't have to be so, they don't have to be too strict about ensuring that the magnetic field is absolutely zero in the region where the atoms are. They can tolerate a little stray magnetic field because the energy levels don't change. So these are the two energy states that they're interested in. How do you make a clock out of that? Well, you can make a clock out of that using the time dependence of the transition between states. And this is referred to as Rabi oscillations after Isidore Rabi, a great American physicist of the last century, who worked out the interaction between atoms and light and showed that there's this time dependence of the transition between states. So if I have two atoms, or I have an atom that has two states, I have this minus X state and the plus X state. If I start in minus X, say, and I put on some light, right, if I monitor what is the state of the atom as a function of time after I turn on the light, what I find is the probability of finding it in the upper state, the probability of finding it in plus X, oscillates at a particular frequency, right? The frequency is now called the Rabi frequency, and that depends on exactly what is the intensity of the light that I applied, what is the frequency of the light relative to the frequency that the atoms want to absorb, things like that. Okay. What this means is if you measure the state of the atom, or if you measure the probability of finding the atom in a particular state, as a function of for many different runs of the experiment, if you measure what that probability is, that will tell you what the interaction time was, right? If you know that the atom started in the minus X state and, it's, now you have a 75% probability of finding it in the plus X state, that tells you that some amount of time has passed, that the atom has been undergoing these Rabi oscillations for some amount of time, and you can determine exactly what that time is by knowing what the Rabi frequency is. Okay. Now there's a further detail to this, which is the way to think about this is not that the individual atoms are making transitions or not, but really this is a coherent evolution which creates a superposition state. So each individual atom is now in some mixture of plus X and minus X, rather than just being in entirely in one or the other. Right? So it's not a probabilistic thing where 75% of the atoms have made the transition, the other 25% haven't. It is every atom has made 75% of the transition, but is still partly in the other state. So each individual atom has some probability of coming out either way. This sort of superposition we can represent as a vector on a circle, right? And so we can sort of define sort of the top of the circle to be one of the two states of interest, the bottom of the circle to be the other of the two states of interest. And then as this process goes on, the state of the atom is we can represent as a vector kind of like the hand of a clock at some angle from the vertical. All right, and if I want to write down what is the wave function there, I would say, well, it is partly in state 2, partly in state 1, and the partlies are related to that angle, right? So the part that's in state 2 looks like the cosine of the angle for the way I've drawn the picture here. The part that's in state 1 looks like the sine of that angle. The probability of finding the particle in state 2 is going to go like the cosine squared of theta over 2. And the probability of finding the particle in state 1 is going to go like sine squared. Right. So this is a representation of this particular superposition state. All right. And this is part of the way that they use this sort of notation and representation to interpret the results of the experiment. Now there's another complication to this, which is that these states are waves. Right, so the plus x and minus x states, or state 1 and state 2, these are quantum waves. They have an amplitude. They also have a phase. Right, they're oscillating themselves in time, and that oscillation needs to be tracked. Right, it makes a difference if you're adding together state 1 that's in its up configuration and state 2 that's in its down configuration. Right, if you're adding those together out of phase, that's different than if they're in phase. Right, so we need to keep track of that. The way that people keep track of that is adding a third dimension, right? So rather than a unit circle, we think about a unit sphere, right? And we think about the state as a vector pointing to a point on the surface of that sphere. And now we have two angles. We have sort of the polar angle theta that's coming down from the top. That's telling us what is the balance between state 1 and state 2. And then we also have this phase angle phi, that's in here. If I rewrite that superposition from the previous, I add sort of a phase factor in front of the state 1 piece of this. That is something that has to do with that phase angle phi. Math detail here. That's a complex exponential function. We'll deal with that in later courses. But anybody who's interested in this should know that. All right, so what are we doing for the experiment? We have these two angles that we can measure, right? So to make the clock, they're driving these Rabi oscillations, and there's two angles you can get. You can get the polar angle by measuring the probability of finding state 2 versus the probability of finding state 1. But the decision as to what counts as state 2 and what counts as state 1 is kind of an arbitrary one. So we would also be free to pick, rather than the north and south poles, we could measure the angles from, say, a point, on the east and west, and measure the angles the other way around. In which case, we can pick two other states, call them alpha and beta in the cartoon here, that are sort of on the equator of this unit sphere at the plus x and minus x positions. And we can get the phase angle from looking at the relative probabilities of the state we call alpha versus the state we call beta. Right. These are deliberately in this picture aligned in the plus x and minus x directions, right? Because those are the states that we're gonna look at. The other two, the ones that are 1 and 2 in this diagram here, are the called plus z and minus z in the experiment, or just an up arrow and a down arrow. So what we can do is we can measure both of these phase angles doing an experiment, and both of those angles are going to depend on how much time has passed. Right? So the basic concept of the clock is we prepare the atoms in a particular state that's represented by a vector that's pointing to a particular location on this sphere. We have them interact with the light field that drives Rabi oscillations between these states and causes these angles to change. Causes the polar angle to change, causes the azimuthal angle to change. We measure those changes in angle, and from those changes in angle, you can work back to say how much time is associated with those changes in angle. So that's the basic idea of the clock part of this. The last piece is how do we get this clock to tick only inside the barrier? And that involves another bit of physics, which is a neat twist on the way to arrange for atoms to make a transition. So the direct method going from the minus x state to the plus x state in this experiment would involve applying microwaves that have a frequency of 6.8 gigahertz. That's a centimeter scale wavelength associated with that. So these are states that you can't really make, you can't really localize those microwaves to, distances much smaller than a centimeter. We want to make a barrier region where this interaction only happens in a space that is, a micron across. The way to do that is using not a direct transition from one to the other, but what's called a Raman transition after Chandrasekhar Venkata Raman, the physicist who first worked out the physics of this. And that is a 2-photon transition using some upper state as an intermediary. So rather than putting on light at 6.8 gigahertz, we take 2 laser photons whose energy difference matches this splitting. So the way to think about it is this kind of goes up with 1 photon. So there's some omega-1 frequency that goes up to the upper state. And then there's an omega-2 that comes back down. So the atom you think of as sort of going up with omega-1 and then being stimulated to emit a photon at omega-2, coming back down to the lower state. This is a process that allows you to drive atoms from the plus X state down to the minus X state or vice versa, provided that you use 2 laser photons that differ in frequency by the energy splitting between those 2 states, by 6.8 gigahertz in this case. And that, it turns out, is a thing that's easy to do using the optical barrier that is the thing that they're going to tunnel through in the first place. So what they do is they make that optical barrier from a laser that has 2 slightly different frequencies in it. And 6.8 gigahertz is a tiny, tiny fraction of the frequency of the green laser that they're using to make the barrier. So they can easily put that in there, and it creates these Raman beams inside that barrier region, and only inside that barrier region. Right. So the atoms interacting with that light are going to both see their energy levels shift, right, which creates the barrier that prevents the atoms from going through. They're also going to see this Raman transition that's going to drive Rabi oscillations between states plus X and plus X and minus X. Right. So this is the perfect tool for this experiment. Right, you can set up these Rabi oscillations to happen due to these Raman transitions only inside the barrier region, only when the atoms are in the presence of this focused down green beam that's providing the barrier that they can't penetrate. And when that happens, then the clock will tick. And then you measure the states of the atoms on the far side. How many atoms are in the plus X state versus the minus X state? How many atoms are in the plus Z state versus the minus Z state? And doing that allows you to work out the angles. Working out the angles tells you how much time has passed, and that gives you a measurement of how much time the atoms spent in the region where they're interacting with this green laser. So that is the classically forbidden region. That is exactly the thing that we want to time, and so that's the essence of this experiment. What are the results of the experiment? This video is already running a little bit on the long side, so I'm going to break it here and leave you in suspense for however long it takes you to click on the link to the next YouTube video in this lecture series.